All right, so today we are dealing with specifically alternating series and proving divergence or convergence by the alternating series test. So for alternating series, these are the ones that have a -1 to a certain power that makes your terms change sign. So it could be a -1 to the n. It could be a -1 to the n plus 1. What's the only difference there? Yeah, in the first one, the first term would be negative. In the second one, the negative would be like the even terms, right? So one of them gives you even terms are negative. One of them would give you odd terms, negative. Okay? All right, so for our example here, that's just whether the series starts with a positive or a negative, even terms or odd terms, right? What this allows us to do is look at certain series that might already converge or diverge. Typically, it's ones that diverge if they are not alternating, that may converge when they are alternating. Okay? So, alternating series converge if the following are true. Okay? Number 1. The limit as n approaches infinity of a sub n equals 0. What does that make us think of? What other test?
P.
The nth term test? Okay. The nth term test tells us that if it doesn't equal 0, it diverges, right? So this one, it's equaling 0, which by itself doesn't mean that it converges. But if we combine that with this fact, the terms then decrease in magnitude. Your notation for that is a sub n plus 1 is less than or equal to a sub n. That's going to be how we show this. Okay? If both things are true, then this alternating series converges. So if you're going through, I would always go through and prove this doing the first thing first and then the second, because if the first condition fails, then the series diverges by the nth term test. So if for some reason the limit does not equal 0, you've now proven that it diverges by the nth term test and you don't have to use separate tests on it. Okay, so you've kind of already done your work for yourself. All right, give you a minute to finish writing those down. Then we'll look at a couple examples. Now, these are more typically seen on free response than some of the other tests. So you do have to actually, if this happens on a free response, show your work for like checking those initial conditions, okay? So we're going to use our limit notation and the terms decreasing in magnitude, little notation there to show that we're actually checking that, okay? It's kind of like when we did IVT and MVT, you just kind of had to state that it happened. So that's where we'll do it for this too. Yeah?
On that quiz on Tuesday,
Mhm.
are we allowed to use the yellow sheet?
No.
What? Can you change your mind?
Nope.
What is it? Is it like the half test quiz?
It's
Double
just a quiz. Yeah, it's like a quiz.
But are we having a half test? Or
No. We'll just
so
do
we
a
should have a
quiz.
full test?
Yeah.
I'd much rather have a full test.
Okay, we'll just do a quiz and then we'll do a full test.
That's actually epic. So it's just one quiz grade?
I don't have time to study.
Flashcard it.
Is it just one quiz grade?
One quiz. Well, it's a double quiz because it's still, every in-person quiz is a double quiz. But that's just because online quizzes are one. But that's it.
Well, I just think of all like technically all.
All right, let's do an example for this. Our first example here is the alternating series, -1 to the n power times 1 over n. Okay? Now, 1 over n, we know, and we've talked about it a couple times, 1 over n by itself, we know does what? Diverges. Okay? So making it alternating might change that conclusion. So we look at two different things. First, we look at the limit as n approaches infinity of 1 over n. That's a pretty easy equals 0, right? You're stating that, but it's also a pretty quick check. Limit as n approaches infinity. Second, we at least show that the next term is smaller than the nth term, basically. And that is the way that you would show the notation. So when we say, I think our wording on this one was with the terms decrease in magnitude, 1 over n is the nth term. You would show the next term after that by making it 1 over n plus 1, right? And for this piece of it, you're not looking at the alternating part of it, because we're kind of taking the alternating part out of this when we're looking at it. We're doing the limit of 1 over n, and we're doing the terms as the 1 over n terms, right? So we have now shown the limit of 1 over n as n approaches infinity equals 0. We've also shown that the next term is less than the previous term. Therefore, we know that the series converges. So although the 1 over n harmonic diverges, the alternating 1 over n converges. Okay. You want to fill that out. So it doesn't take us real long to check those two things. It's a pretty quick go through those two, check what's going on, make sure whether it does or does not work. Okay? All right, so if I'm going to look at example 3 on the back here. All right, so if I'm looking at the alternating series, n plus 1 over n. Harmonic diverges, but alternating harmonic converges. So I check the limit as n approaches infinity of n plus 1 over n. Think Bobo button eats DC. Real quick, that gives me 1. Do I keep going? No, this doesn't equal 0. So what does this mean? It diverges by the nth term test. So this is why we always check those conditions in order, because if that does not work, we do not continue. And it already gives us a different conclusion. Real quick. All right. Now, I need to skip a couple pages here that we're going to come back to. My PowerPoint kind of got in the wrong order here that I want to go through this one next. Okay. So, that's not working. Good. Cool. There we are. All right. This is your example 4, correct? Is this your example 4? Yes. Okay. All right. First off, does this look like any of the other alternating series we've looked at? No, it's a little bit different, right? So some of these we've talked about having to like rewrite this to look correct for us to make our conclusions about it. So I've got to do a little bit of rewriting on this. What do I really need to separate out? I need to kind of take that -2 and pull it into pieces. What's the best way to do that? You can separate it into 2 to the n and -2 to the -1, but what we really need to see to make this an alternating series is a -1 to the a power, right? So is it okay to take it and do this with it? All we're doing there is we're taking and we're separating the -1 that was multiplied by the 2. We're leaving it to the power n minus 1. And we're keeping 2 to the n minus 1 by itself. Has that changed the problem at all? No. I mean, that hasn't changed anything. Remember when we were doing geometric, we said we could kind of take that and pull powers in pieces for the geometrics? That's the same thing we're doing here. Just because you do it when we're doing like division, it felt a little bit more comfortable. Multiplication, though, works the same way. That if it's to the same power, you can then combine those together as a -2 to that power. So pulling it in those two pieces means that this is now an alternating series. Now that you've shown it as an alternating series, we can now check. What's the first thing we check? The limit as n approaches infinity of just the a sub n part, not the alternating part. So what are we taking the limit of? N over 2 to the n minus 1, right? This is the piece we're taking the limit of. Take a minute on your own papers and find the limit of that as n approaches infinity. Now, do you have to show your L'Hopital on this? Probably not.
Just say equal to 0.
Right.
So you don't do L'Hopital's?
You use L'Hopital, but you probably don't have to show all of the work for it. Can you tell just by like common sense what this limit's going to be?
0.
Yeah, I mean the top of it's going to increase so much slower than the bottom of it that this is going to approach what? 0, right? Now, because of that, I mean, you don't have to show all of it. If you want to, do it. And we'll talk about this as we get to free responses more. But you would use L'Hopital on this because right now this would be indeterminate form. L'Hopital, though, would make the top 1 and the denominator 2 to the n minus 1 times the ln of 2, right? And that's really where you'd be getting your 0 from. But generally, as long as you're checking these conditions, you could go directly to that limit as n approaches infinity is going to go ahead and equal 1. All right, so we've got the limit as n approaches infinity of n over 2 to the n minus 1 is going to equal 0, yeah? What else do we check? Yeah, do the terms decrease in magnitude? Okay, so to show that, we put in place of all of our n's, n plus 1's, right? So we would say n plus 1 over 2 to the, if I make that n plus 1, what's it really going to be? N plus 1 minus 1? Just n? Go back. Is less than or equal to what? N. Is this a true statement?
Yeah.
Well, again, think about the increasing, okay? If we go from this to the next term, n to n plus 1, that's certainly getting bigger. You're adding 1 to it. But think about it going from this one to this one.
We're getting divided by 2.
Yeah. So like going from 2 to the n minus 1 to 2 to the n, you're multiplying by another power of 2. So isn't the bottom increasing much more than the top is when you add 1? So that is truly smaller then, yes? So once we check those two, that means what?
Wait, I have the. Which one's bigger?
This one is bigger than this one because the denominator gets so much bigger here that it makes the fraction smaller. Okay? So we know this series converges, yes? Now, there is a way with alternating to talk about a series converging a little bit easier than showing these 2 steps every time. And if there's any shortcuts, we always want to take those shortcuts. Yes? Okay? So at this point, before we go on to other examples, I want you to flip over to page 350 real quick. Okay, flip over to page 350.
Hold up, Miss Nagel, we skipping that.
I know. Your notes are in a little bit different form than mine are. All right. In alternating series, we talk about something called absolute and conditional convergence. So we're going to write down this to just begin with, and then we're going to go forward, okay? So we call a series, an alternating series, absolutely convergent if the original a sub n series, not alternating, converges. So this allows us to shortcut this process slightly. If the a sub n series converges, then both it and the alternating will converge. And we call that absolutely convergent. So a good example of that is the 1 over n squared series. How do we know 1 over n squared converges? Based off of p series, right? So if I just look at that 1 over n squared, I already know 1 over n squared converges by the p series, right? Because the original a sub n, when it is not alternating, converges, the alternating series also converges. And this is something that you can actually state. So because 1 over n squared converges, then your other one would converge. So we would call this absolutely convergent. Yes?
Do you use the word absolutely convergent in notation?
Yes. You would say because 1 over n squared converges, this series converges, or it is absolutely convergent. Yes. Then we have what is called conditional convergence. Can you guess what that is? If the original one does what? Diverges, but the alternating one converges. Yes. So it's conditionally convergent if the original a sub n diverges, but the alternating version converges. We already looked at one example of that. Which one was that? The harmonic. 1 over n diverges, but the alternating 1 over n converges. Another example would be 1 over ln of n. 1 over ln of n diverges on its own. However, by our alternating series, the limit of that is equal to 0, and a sub n plus 1 is less than a sub n. So then that alternating version converges. Okay. Once you've finished filling that in, we're going to go back and look at example 4 that we just finished. Because I bring it up after that example to show you we could have done that in example 4. Okay. All right. So looking back at example 4, if you look at this original a sub n, what does our common sense tell us about n over 2 to the n minus 1? Yeah, it converges because the bottom's an exponential, which is always going to increase so much faster than a linear, right? So n over 2 to the n minus 1 would be convergent. Therefore, you could have immediately said this whole thing converges because the original a sub n converges. This one is absolutely convergent. So that is a shortcut if you see it. If you don't see that, showing the 2 steps will still work. But it is a shortcut, and anywhere we can have a shortcut is nice. Yes? All right. Let us take a look at the next example here, number 5. All right, number 5 looks a little bit different, yes? So the last one we had to rewrite just a little bit to make it a alternating series. I don't see anything in example 5 that I can make a negative 1 to the n or n minus 1. Like I can't split anything up. So let's reason this out real quick. Take a look at the cosine of n pi. Think about the cosine function. If n equals 1, you're doing the cosine of what? Pi. What's the cosine of pi? No. Negative 1.
Yo.
If n is 2, you're doing the cosine of 2 pi. What is the cosine of 2 pi? 1. If n is 3, it's 3 pi. Back to pi. So what is the cosine of n pi really doing? Yeah, it's oscillating from negative 1 to 1. That piece right there is what makes this an alternating series. Okay? You do not have to prove that. They just expect you to recognize that. So anytime, and for those who like your little notes on this, anytime you see cosine of pi times n, that is always the same as -1 to the n power. It means the same thing. So, what do we have to check then? Limit as n approaches infinity. What are we doing the limit of, though? Because remember, when we do the limit, we don't include the alternating piece. So really, you're just doing the limit of 1 over n minus 1. Right? And that's why it's important to recognize that cosine of pi n as the alternating piece so that you don't have to include that in your limit. Right? So we know that limit equals 0. So far, so good? All right, what's the other thing we check? Are my terms decreasing in magnitude? Yeah. How do you write that for 2? 1 over n is less than or equal to 1 over n minus 1. Yeah, that's accurate. And that's a true statement. You could also just sometimes say terms decrease in magnitude to show that you've actually checked that. Therefore, because the limit equals 0 and our terms are decreasing in magnitude, what do we know? This converges. By the alternating series test. All right. 1 over 1 like this, and then one other one like this in example 6. And then we are quickly going to talk about alternating series error. Okay. All right. So this one is, 6 is pretty similar to 5, except instead of a cosine, it is a sine. All right, so let's reason it out. If n is 1, you're taking the sine of what? Pi over 2. What's the sine of pi over 2? 1. If n is 2, you're taking the sine of 3 pi over 2, which is -1. So it does 1, -1, 1, -1. Okay? So which piece is making this alternate? The whole sign, right? So for just your notation, you're going to see the notes are a little bit different. The cosine of pi n, you will typically see that, and that is the same as the -1 to the n. The sign notation you see there is the same as -1 to the n plus 1, because that starts positive rather than negative. Okay? So when I check my limit as n approaches infinity, I'm doing the limit of what piece only? Yeah, the front one. The 1 over n plus 1, right? I don't include the alternating piece. We just do 1 over n plus 1. Now, do I have to do this whole thing?
No, because the
What do I know about 1 over n plus 1?
absolutely convergent.
This will make it absolutely convergent because 1 over n plus 1 converges. The alternating also converges. Could I have done that on the last one?
Yeah, you could.
Yeah, I could have. They're both kind of P series. 1 over n minus 1, 1 over n plus 1, same thing. Doesn't really change. But you can go straight to series is absolutely convergent. Typically, if I said absolutely convergent, I would make a statement about the sum.
Wait, so why did we do it?
Because if the sum of the non-alternating one converges, then the sum of the alternating also converges. That's called absolute convergence. That's what we just talked about on page 350. So if you can show that the sum of the a sub n without the alternating converges, you can say that the alternating one will also converge.
But you still have to like make the statement of why it converges, because doesn't it converge?
That one, that would be P series. Yeah. All right. The final thing we're talking about today is going to be the error. Did you have a question?
Wait, why didn't you take the limit?
why did I need to, or why didn't I?
Why didn't you?
So, page 350 that we talked about with all absolute and conditional convergence says that if you can prove that the A sub n series converges, then the alternating one automatically converges. So we would do that purely if we recognized that the A sub n series converged. It doesn't work for divergence.
What does it say about the series?
I was going for infinity there. 1 over n plus 1.
Limit diverges because of C series.
Converges?
Cause you,
Oh, wait. Hang on. Yeah. Where's my, clear my drawing on that one. 1 over n plus 1 would have diverged by p series. That one, I think we just skipped the work on it. We probably should have just done the limit as n approaches infinity of 1 over n plus 1 equals 0.
So it's not absolutely convergent?
No, I think I went with it because hers went directly to that without showing the work. But I shortcutted where I should not have shortcutted. Not absolutely. Thank you. I'm sorry. I occasionally say things incorrectly, especially in this unit.
Is there the alternating from minus? The alternating from minus?
Yeah, this would be like the alternating harmonic. So in this case, you would have to show the limit equals 0, which it does. And you would also have to show 1 over n plus 2 is less than or equal to 1 over n plus 1 would be your notation for that one. I jumped straight into that without thinking. Should not have. Now, to practice our idea of converges conditionally or converges absolutely, and hopefully I don't screw this part up, okay? Let's just look at this set, which is not in your notes. Okay? Take a look at question 1. How do I tell if this converges absolutely or conditionally? What do I look at first on question 1? The 1 over 2 to the n. I ignore the alternating part. I look at 1 over 2 to the n. What do I know about 1 over 2 to the n? Converges. Therefore, what do I know then about 1? Absolutely converges. All right. What about question 3? What am I looking at to tell? 1 over n factorial. What do we know about n factorial?
it's so fast.
That's so fast, right? So that's going to converge, therefore, converges absolutely again. What about 1 over n plus 3 squared?
Are these slides on campus?
If they're not, I'll put them there.
That's gonna,
Converge.
What am I thinking about for 1 over n plus 3 squared?
that'll be an n squared.
That's like a p series. It's almost like 1 over n squared. Therefore, what does that do? Converges. Therefore, the whole thing converges absolutely. What about 1 over root n?
Does not converge.
1 over root n would not converge.
Diverges.
So the original diverges. That does not mean the alternating one diverges. What would I have to do? I'd have to do the limit as n approaches infinity of 1 over n. What would be the limit as n approaches infinity of 1 over n? That would be 0. Are my terms then decreasing in magnitude? Think about that.
Yes.
Yes. So what would we say about this one?
Concierge.
Converges conditionally.
I think you converge conditionally.
All right. What about n squared over n plus 1 squared? What does your gut tell you about that?
That's gonna equal c.
Boa body needs DC.
Right.
Diverge.
So I'm going to be able to show that the n squared over n plus 1 squared diverges by nth term test,
But then
right?
it would converge conditionally.
Would it?
I believe so.
Well, think about the limit as n approaches infinity. Is that going to be 0? So remember, if the limit doesn't equal 0, you stop the alternating series test. Because what does it do?
It will diverge.
It diverges. So this whole thing diverges. Okay? What about 1 over n times ln of n?
That's divergent. That's like super.
That's one, remember when we first talked about the common sense thing? We talked about the 1 over n times ln of n being kind of really where it splits. That one diverges originally. So how would I show if it converges conditionally? I would check the limit as n approaches infinity. That would be what? 0. Okay. And then we would check the terms. Does it make sense that as n gets larger, each term would be getting smaller?
Yes.
Yeah, because there's no n on top, right? So that's a conditional convergence. What about n over n cubed minus 5? What does the original do? That would converge because the n cubed is going to get, that's mostly like a 1 over n squared, right? Similar to p series, 1 over n squared. So what about, if that one converges, what do we know about the alternating one? Converges, absolutely, yeah? All right. You should be able to not even have to reason out the next one. Convergent. Absolutely. Anything with the factorial.
Oh, we just did this one, Miss Lauren.
We did.
That would converge.
So the original would do what?
Diverge.
Diverge. So then this one would
Converge.
converge conditionally. Okay. What's the original on the last one? 1 over n squared?
Absolutely.
Okay, so that means this converges absolutely. Okay? So that can start to flow with your common sense stuff as we go. Like I said, I screw those up occasionally, but that's fun. Okay? All right. Very final things here. Alternating series remainder. Okay? This is our very last page, page 349. One thing that we talk about as we get further into this unit, and this is kind of where the second half of the unit goes after the quiz too, is error. Error is essentially kind of, a lot of these things are estimates. We have ways of getting sum of geometric series, but we haven't really talked about sum formulas for any of the other ones. So a lot of times we estimate the sum of a series using a first few terms. So we would call our estimate S sub n. This is obviously not the exact sum of the series. It's just a decent estimation because eventually, especially if a series is converging, those terms are not going to make a huge difference the further out you get, right? So the exact sum would be S. So if an alternating series converges, and therefore the terms are decreasing in magnitude, then what we're going to call the remainder or the error involved is always going to be less than the next omitted term. Now, write that down, but we're going to kind of talk through what that means. I know, it's a little bit off. I'm sorry.
Did you say that was a remainder?
Okay, this will make more sense when we look at an actual example with numbers. So take a minute to fill it in. Yes, the next omitted term. I don't know why the spacing is off here. If I do it on my computer, it all works just fine, but this looks real wacky.
Also called the.
So write down what's in that box as well. That goes in your box as your formula.
Also called the error, bro.
I already wrote it.
So S sub n minus a to the n, or a sub n minus 1, n plus 1, excuse me, is less than the actual sum, which is less than or equal to
Less than the next omitted.
the estimate sum plus the
Is it
next omitted term.
What term? Or is it omitted term?
Omitted term. Less than the next omitted term. All right.
Omitted. We don't say omitted.
Do we have everything filled in up through the box? No?
There's so much happening.
Pausing. Pausing.
Okay, no, no, no.
All right. Now that formula is going to stay
Wait, it's like,
at the top of the next page.
I didn't.
Too busy saying error in robot voices.
I didn't realize that we had that, I didn't realize that we had to write that part down. The whole slide is off.
So, what is
That's a
all
big
this?
dog.
What is all this?
Well, I told you it'll make a whole lot more sense after we do an example. I promise.
Well, let's do it. Right
All right. Here's our example. Okay. So here's our formula. We're going to keep our formula here for you. This is less of a proof, more of an explanation. Okay? So we are going to use the following series. We're going to use the alternating series, the alternating harmonic series to prove this. Okay? So just write this down. This is our alternating harmonic series. It begins with -1 plus 1/2 minus 1/3, blah, blah, blah. This is out to like the 7th term. Dot, dot, dot. Okay. Now, we have no formula to give us the exact sum of this. So far, the only thing that we have an exact sum for is the geometric series. That's that a sub 1 over 1 minus r. Most of these, we will be estimating the sum by saying, add up the first couple terms. Because again, if this converges, eventually these little teeny tiny fractions going out to infinity are not going to matter. So, the example could be on this one, talking about an estimated sum using the first 4 terms. Okay? So if you are asked to find an estimated sum of the first 4 terms, we would literally take and add up the first 4 terms. So we would say -1 plus 1/2 plus -1/3 plus 1/4. This would be our estimated sum. We would call that S sub 4 because it is the estimated sum using the first 4 terms. So this is what this tells us, the paragraph above. If this is truly an alternating series, terms are decreasing in magnitude, this estimate is only going to be off from the actual true sum by less than the next omitted term. What is the next omitted term right after that box? 1/5. And we don't even need to worry about the negative. It is just the 1/5. So the true sum of this series is only going to be off from that estimate by less than 1/5 on either side. We'll call that my remainder. The remainder would be all the rest of that. Do we really have the ability to find the true remainder? No, just the way we don't have the ability to find the true sum. Okay? So what we know is this. The true sum would be those two things put together, yes? Which we can't find. But what we know is the 5th term, 1/5, is greater than or equal to the sum of the rest of the terms. Okay, we know that fact. We know the 5th term, according to this, is greater than or equal to the sum of the 6th on out. So we know that our error is going to be less than the difference between that. So if we set up an actual equation for this, I'm just going to pull out a calculator for you, okay? if we added up the first four terms, our first four terms are -1 plus 1/2 minus 1/3 plus 1/4. Yes? So my S sub 4 is -7/12 if I add up all of these. Yes? So here is what this whole thing tells us. We know for a fact that the true sum of this falls between -7/12 minus 1/5 and -7/12 plus 1/5. Now, as you might imagine, the further out you go, what do you think is going to happen to the error? It's going to get less and less, right? Now, sometimes the error is already small enough, like this is within 0.2, right? Because that's 1/5, 0.2 on either side. Right. So that's not maybe that accurate for us. Maybe we want our error to be even less than that. So the way some of these questions are worded are for you to look at this series and decide how many terms you have to go out to have your error be less than a certain amount. So you have to keep looking at the next terms to decide how small you want it to be. Sometimes it will ask for a specific term. Other times it will tell you, you find how far you have to go out to have your error be less than 1/100th or 0.001 or something. So you're going to essentially look at the terms and say, where do I cut this off so that the next term is less than whatever they want it to be? Yep. Okay, now I'm not going to do the math of like that exact, but does that make a little bit more concrete sense what we're looking at here? Maybe? All right. So we're going to use this for a couple different things. One is the last thing that we're going to write on this page. Then I'll be done. We are often going to estimate the sum of an alternating series. This is like the exact same thing. I'm not really, that omitted has 2 M's in it. Don't write that. I know I don't like that. Whoops, go back. All right. And we'll do one example with this. That formula is kind of a little bit like a lot to memorize. So you often just want to think true sum is between estimated sum plus or minus the next omitted term. That's kind of the English language way of memorizing that rather than memorizing a formula. Okay? All right, so we'll do one example with this. We'll fill in our things on our yellow sheet to make sure we're ready to go up through the alternating series, and then we'll be done. Okay? All right, so.
Is the quiz next time?
No.
Is that next week?
Next week. All right, so the example tells us to determine the sum of the series using the first 5 terms. Okay? So if we would like to find the sum of the series, the first thing we're going to do is find S sub 5, right? So how do I find S sub 5? Yeah, think about the first 5 terms. So what's the first term? -1 plus 1/2 minus, okay, plus 1/4 minus 1/5. All right. Yes. But we did the first 4 terms, so we're just calculating it slightly differently. All right, so since I know you'll trust me on the calculations of this, rather than make you pull out your calculators, we add all that up. If you write it as a fraction, it's -47/60. If you go just to 4 decimal places, it's -0.7833. So this is our estimated sum. So now I want you to think about, how do I set up my range of values that the true sum falls between? What do we know? The true sum falls between what? Okay, so the next omitted term would be 1/6, right? So we would say our true sum falls between that minus 1/6. For the next omitted term, no. So when you add them up for the S sub 5, yes. But the next omitted term, you're subtracting it on one side and adding on the other, so you don't include the negative. And then on the other side, it's negative 0.7833 plus 1/6. Yes? So you know your true sum falls between those. Your error is less than the next omitted term. So that's that 1/6. So in decimals,
It's like standard deviation.
it's very much like standard deviation, yes. In decimals, that would be like negative 0.95 on the left and negative 0.6166 on the right. So it's a pretty close range, even with only going out to 5 terms. If the terms decrease in magnitude even quicker, like if it wasn't just going 1/2 to 1/3 to 1/4, if it was going 1/5 to 1/25 to 1/625th, it would be more accurate faster, right? Does that make sense generally?
Yes.
Okay. Those will be a little bit of the trickier questions on the homework. I do expect to talk about them because this is something a little bit different than what we've talked about so far. Okay? Yellow sheets real quick. What do we need to have filled in under our alternating series here? What do we need to fill in? Nothing? Yep, I would say check the limit as n approaches infinity of a sub n. That must equal 0. I would also say a sub n plus 1 must be less than or equal to a sub n. Okay. Any other special notes we need to have on this one?
Absolutely conditional.
Mm-hmm. Absolutely convergent. If the sum of n equals 0 to infinity of a sub n converges, right? It stopped writing, but it'll catch up in a second. Conditionally. I don't know why it's doing that. Nothing.
Can you just read off what you have?
Yep, I said it's absolutely convergent if the sum from n equals 0 up to infinity of a sub n converges. Right? The original without the alternating. Yeah? I don't know. Hang on.
Oh, there it is.
There, now I can. All right.
Okay, you left them?
I knew we were talking about
I just remember doing the I think I wrote a picture of Gene or something.
it.
I didn't actually get the
What conditional?
I would just put if a sub n diverges and the alternating series converges. Wow, this is really like freezing up on me today. I think it's because my video's too long.
Okay, conditionally convergent if it.
If the original diverges and the alternating converges.